In the last segment, we took a look at the different forms of condensation, and we said that there is film or droplet condensation. And we also said that droplet condensation was the more efficient from the heat transfer perspective. Now, in order to achieve droplet condensation in systems, quite often coatings will be added to the surface. And what these coatings do is they have an impact upon the surface tension characteristics between the solid and the liquid that is being condensed. And so coatings such as silicones, Teflon, waxes, and fatty acids, those are examples of coatings that will change the surface tension characteristics between the solid and the liquid, and that helps prevent film condensation, and then it enables droplet condensation to occur. Now, when we're doing engineering calculations, typically what we will do is we will assume that film condensation is occurring, and that gives us a bit of a factor of safety in our engineering design calculations. And it's basically a worst case scenario type of estimate for the calculation. So you wouldn't be undersizing a condensing unit, for example. Okay. So, and what we're now going to do, we're going to take a look at some engineering applications where condensation is quite prominent and is used in part of the system. So what we're going to do, though, we're going to begin with the most general, and that's looking at condensation that we experience in our everyday lives. And so what we're going to begin with, here we can see condensation on the window of an automobile that has been placed outside overnight, and when it gets cool at night, the condensation occurs on the surface. There you can see some more condensation on a mirror, and you'll see the droplets form together and then they run down the surface. Now in Calgary, in northern climates, sometimes what happens is it freezes, and there you can see evidence with frost patterns form, and essentially what's happening is the moisture in the air condenses and then it freezes. This is an example in China where the floor is actually below the dew point of the atmospheric air, and so what happens is you get puddles forming on the floor due to the fact that the floor itself is cooler than the dew point in the air, and you have condensation occurring on the surface. So sometimes what they do is they'll put cardboard down, and that minimizes people from slipping while walking on surfaces like that. But if you're walking around in China or other very, very humid climates and you're wondering why the floor is wet, that is probably the reason. It's due to condensation. Now, another type of application that we're going to look at is that of the heat pipe, and so heat pipes are used in many different types of applications now, and we're going to begin with this one. This is a bubble light, and it has methylene chloride on the inside. On the right we have high-speed video. You can see there is boiling occurring, the bubbles are moving up, they get to an interface, and then there's condensation from the tip that then runs back down. So with the IR camera, we can see the bulb temperature is around 57.5 degrees Celsius. And then we can go into the stem region, and the temperature drops down a bit. It's around 41.6 degrees C, where the bubbles are rising up. And then at the tip, the temperature is around 39.7 degrees Celsius. And when you look at the saturation temperature for methylene chloride, it's 39.75, which agrees very, very well with what we're seeing. And so it's because there is condensation of the methylene chloride occurring on the inside of the tip. And it would make sense that we would be measuring the saturation temperature within that device. So the bubble light is a bit of a novelty. It's an interesting thing to look at. But that very same system is used in many engineering applications. And so what we're going to do now, we're going to take a look at a few of those. And we're going to begin with computing. Computers. Processes generate enormous amounts of power and heat. Well, they don't generate power, they generate heat. And we have to dissipate that. And so these are coolers that are used for central processing units. And they're a bunch of different varieties of shapes, sizes, but you can see the heat pipes there. They're the copper pipes that are coming up into the fins. There it is on the side. There you can see the top of the heat pipes that extend up through the fins. And then there you can see the side profile again with the heat pipes going up. So essentially this is the same as the bubble light, but inside you would have a working fluid that would boil and then it would go up and condense and come down. And so what we're doing here is an experiment where we put that heat pipe apparatus onto a hot plate. Heat is on, and so it's heating up. I have a fan blowing through it in order to provide cooling because otherwise it would overheat. And then when you look at the heat off, what's happening is the fluid in the pipes is cooling off due to the fins, and so you can see the fact that the temperature drops as the pipes go to a lower and lower temperature. This is a railroad in Shanghai to Tibet Railroad, and there are heat pipes on the side to deal with the permafrost. And here's a similar application in Alaska where we have heat pipes. And what they're doing, if there is anything on the surface in permafrost, they put those heat pipes under the surface, and that maintains a low frozen temperature of the permafrost, and so it doesn't thaw. And if it thaws, what would happen is the railroad would either sink or it would shift, and you'd have all kinds of geotechnical problems going on. So heat pipes are used not only in computers, but they're also used with pipelines or railroads like we saw with that one particular application. Now, another application that we have for condensing is in refrigeration. And so here is a picture of a refrigerator. It's an older fashioned refrigerator where we have coils on the back. But what's happening on the inside of those coils is we have condensation occurring. So the refrigerant becomes a superheated vapor after the compression process, and then we reject heat and it's going through a condensing process. And so that's essentially what we're looking at as the refrigerant flows through those coils. And so that would be where you have condensation on the tube side. The condensation is occurring within the tube, and it's going from being a superheated vapor down to the saturation temperature, and then it would go through a phase change, and then you would have a liquid coming out at the bottom. But that is typically the cycle used for any kind of refrigeration system. And then finally, the last application that we're going to look at are very large-scale industrial condensing units. And so here we can see a picture of a condensing unit being fabricated. Sometimes it's hard to tell the difference between a condensing unit and a shell and tube heat exchanger. They're very, very big, and you got a lot of tubes on the inside. But in this particular one, this was one where it was tube-side condensation. And so they are relatively large tubes. The tubes there, they're probably 1.5 to 2 inches in diameter. And so what is happening is you have condensation occurring within the tubes. And if I sketch that out, you would have a system like this. And usually they'll incline the tubes at a bit of an angle, but you would have a vapor going through. And you would get condensation forming, and you would get a film forming like this. You want to use gravity to draw that down. Sometimes you'll also have your vapor, so you have velocity vapor coming through the central core. But essentially what happens is this here would be your liquid, and you would have gravity driving that. You want to be careful because as the tube gets with more and more liquid building up, so eventually you're going to get to some point like this. Ideally, you want to keep it as being stably stratified flow. And so you'll have your vapor up here going through. This is if we have what we refer to as being tube-side condensation. You need to be careful because what can happen is if the vapor velocity is high with respect to the liquid velocity, so this is our liquid here, you can actually get instability waves that start to form on here, and that can transition into slug flow, and it could cause a very, very high pressure drop. A multi-phase flow physics can be rather complicated. Now sometimes you're okay with this, but sometimes you're not. For example, if the vapor has to go through another stage, ideally you don't want to be entraining liquid droplets like you would get with multi-phase flow or plugs coming out of it. So anyways, those are examples of condensing units that are used in industrial applications, as well as many other types of condensing applications that we use in not only in engineering but also that we see in everyday life. And so what we're going to be doing in the next segment is we're going to be taking a look at some of the correlations. We'll derive the Reynolds number, and then we'll move into some analysis that Nusselt did, coming up with very early correlations enabling us to determine the convective heat transfer coefficient for these types of systems.